record. There we go. Okay, so we just covered what the squirrel cage looks like. Okay, so as we said, there's a couple drums with metal bars, magnetic fields, or revolving magnetic field hits it, inducing EMF. EMF induces motion, and because it can't go sideways, it's going to try to go sideways, but it's going to go in the rotational motion because that's the way it is mounted. Now, instead of having those metal bars across those drums, you can substitute those with the windings as well. Instead of the metal bars, and you're going to get the same effect as the squirrel cage. However, you can, well, the biggest difference is that when you have just a squirrel cage, you can only use that machine as a motor, all right? Because you don't have any windings. You just have a couple of drums, a drum, a couple of discs, and you have the metal bars, and you can make that move. And that's it. There's nothing you can get out of it as far as if you try to use it as a generator, right? Now, if you have a wound rotor, you arrange the windings in a similar way as if you were having those metal bars. However, you can get the windings out into something that's called a slip ring or slip rings. It's just like a form of a commutator. A slip ring is a ring with a brush around it. And the reason why we use the slip rings is that if you have one axle, and you can have one smaller slip ring, and you have an axle that kind of hugs it, and you have a bigger slip ring around it, so you could have two terminals on that. Okay, so then in this case, you can get two things. You can sort of excite those if you want to magnetize them, but usually it's not being done. However, if you have that arrangement, then you can use that sort of as a generator, or those type of motors usually are not being used in generating power as far as per se regenerating power. So if you have an electric car, you can use that when the car, you just take the step, maybe just take your foot off the gas pedal, all right? Then the motor is not powering up the car, but you still have the kinetic motion, kinesthetic motion going forward. So you can use that as a generator, and you're going to have some sort of EMF generating inside those in those windings, and you can grab some of it. All right. So so the difference between the squirrel cage and a wound rotor is one uses the metal bars, and it just looks like a squirrel cage, and the other one also basically involves the same principle, the same idea, but instead of the metal bars, you get the windings, which you can connect to something and get something out of it. So you can use it as quote unquote regenerator. All right. I hope I answered your question with that one. All right. I don't hear no, so that no means yes. I mean, no means yes. All right. All right, so there we go. All right, so what do we have here? Just grab the proper mouse here. All right, so stator 3, it's just like the synchronous motor. So in the stator, you are going to have something that's called a synchronous speed. All right, so that synchronous speed is going to exist in the induction motor. Right? And the synchronous speed is the speed of the revolving magnetic field. Okay. And so here's the rotor, two types, squirrel cage or wound rotor. Okay. Now, asynchronous here. So the induction motor is also called as asynchronous motor, okay, which means we're talking about the rotor speed and the stator field speed. So stator has the stator windings, and we have three-phase electricity, three-phase voltage or current, three-phase power applied to it, which produces the revolving magnetic field, and it's going to make the rotor turn. Okay. Now, over here it says not the same but close. All right. Just as a review, how is it that the rotor speed or the revolving speed or the turning speed, right, is not the same as the synchronous speed? As we were talking about this, the three-phase power that is applied to the stator windings is do I have it? Yeah, okay. Is creating the revolving magnetic field, and the magnetic field revolves at something that's called a synchronous speed, and that cannot be changed unless you change the frequency of the power applied to those three windings. If you change the frequency, yes, you're going to change the speed of the rotating magnetic field or the synchronous speed. But if the frequency stays the same, that thing will never change. The synchronous speed is unchangeable if the frequency doesn't change. All right, now, so what happens, same as the wound rotor or squirrel cage rotor, just imagine that those metal bars are going to be hit by that rotating magnetic field, which is going to induce EMF, which is going to induce the motion. So there has to be a difference in the speed for that thing to work. Because if the metal bars were revolving at the same speed as the synchronous speed, then those metal bars will not be treated with the changing magnetic field. It would be just exposed to the same strength of magnetic field. And we know that in order for EMF to be induced in the conductor, there has to be a changing magnetic field hitting it. All right. So let's just say the rotor is going to start rotating and is going to achieve the same speed as the synchronous speed. Well, then there will not be changing magnetic field applied to those rods, which means there's going to be no motion induced, which means that rotor is going to lose the momentum. It's going to lose the power of turning, right? Which is going to slow down a little bit. But as soon as it slows down, then the speed differences are. So then as soon as it slows down just a little bit, then there's a changing magnetic field hitting that metal bar, which is going to induce the EMF, which is going to induce the motion, and it's going to speed it up. So it's going to be just a little bit less. Always it's going to be less. The rotating speed of the rotor is going to be always a little bit less, because as soon as it hits the equality, as soon as it goes equal with the synchronous speed, it loses the power of turning. So it's going to slow down. It's going as slow, and then, okay, as soon as it slows down, okay, I could just go in circles doing that kind of stuff, right? So if someone doesn't, if someone has still troubles grasping this concept, by all means, email me, okay? All right, let's keep going with this. All right, so we have the three-phase winding, squirrel cage or wound motor, rotor speed versus the rotor speed versus the stator speed, which is the synchronous speed. They're going to be not the same, but very close. All right. Working principle: revolving fields as the synchronous speed, and here is the formula that we have used before. The synchronous speed equals 120 times the frequency divided by number of poles in the rotor. Okay. Now, in order to change the direction, and we have all experienced that in our labs, in order to change the rotating direction, can anyone tell me? Sure, you can. You can just read this. Right? Switch any two phases, and that is going to make the rotating magnetic field or revolving magnetic field change the direction to the opposite. Yeah? Now, rotor induced voltage, induces current, induces torque, and then there's the rotating speed with the designation of the letter N. Okay. All right, so now we're going to talk about the slip. Remember when we were talking about the rotor speed is going to be always less if we use this as a motor. Okay, so the rotating speed of that machine, of that motor, is always going to be little tiny bit less. Right, it will never reach the same speed, and we talked about that just a few seconds ago. All right, what do we have here? Let's analyze this slide here. Stator, revolving speed, synchronous speed. So we got the formula already here. Rotor speed, not the same, but close to the synchronous speed. All right, and here is the formula for something that is called a slip. All right, so the slip is, here's the formula, and let's just analyze this formula. So it's going to be the synchronous speed minus the actual rotating speed of the rotor. And if you divide that again by the synchronous speed, you're going to get a fraction. And then if you multiply that by 100, you're going to get the slip in the percentage, as a percentage. All right? So let's say, Mr. Odi gave us example here. Example number 1, a 6-pole induction motor is powered by a 3-phase 60 Hertz source. If the full load speed is 1140 RPMs, rotations per minute, calculate the slip. All right, so how we approach that? We need to know, what do we need? We know the actual rotating speed. So that is, we have that given. We also know the frequency. Based on that, we can calculate the synchronous speed. All right, so here's a synchronous speed equals 120 times the frequency divided the number of poles. So we know there's got 6 poles, divided by, where are we? Okay, so 120 times the frequency times 60, there we go, divided by 6 poles, and that is going to give us the 1200 RPMs, all right? So we have the synchronous speed. Is it bigger than the actual rotating speed? Yes, it is bigger. So, excuse me. So by now we can just confirm that the whole law of physics and us being on this planet still applies to us here. Okay, so we're good. Things are concurrent with what they should be. All right. So let's calculate this slip based on that formula. So we're going to go the synchronous speed minus the rotating speed over the synchronous speed, and if we plug in the numbers, we're going to get something like, it's a fraction. It is 0.05. And well, what is the unit? Well, there is no unit because those units are going to cancel out as we plug the numbers with the units into the equation. So we're just going to get that number. And then, of course, if we multiply this by 100, so we can say that this motor has a slip of 5%. Okay. All right. Next slide, analyzing this. Synchronous speed. Here's the formula. Then the slip, we got the formula as well. Slip, okay, speed difference, and a ratio. So we are considering the difference of the speed, which is the difference between the synchronous speed based on the frequency and the number of poles, and we can apply the ratio to that. So it's a ratio between the speed difference and the synchronous speed. So we got that. All right, stator, apply three-phase electricity, frequency, revolving magnetic field, speed. Here's a synchronous speed with the designation of N with a tiny little bit of a S right beside that. All right. So let's just consider a couple of scenarios here. Rotor at the standstill. All right. What is going to be the slip? okay, when the rotor stands still? Well, the rotational speed is 0 when the rotor stands still. Okay, so we got that. The synchronous speed, whatever it is, we're not even calculating it here, because when we plug in the um, synchronous speed, so we have the synchronous speed minus 0. So we're going to end up dividing synchronous speed over the synchronous speed, and we are going to end up with the number 1 multiplied by 100. And when the rotor stands still and the machine is turned on, of course, we're going to have a 100% slip, which means that the rotor is not turning. Okay. All right. Let's say if we had the synchronous speed, so we're going to have the rotating speed equal to the synchronous speed if the rotor turns at the synchronous speed. So of course, we're going to have the plug in the numbers in the formula. So we're going to basically subtract synchronous speed from the synchronous speed. Of course, we're going to get 0, and 0 divided by anything, we're going to end up with the 0. So if the rotor was turning at the synchronous speed, we would have the slip value of 0%. I think it all kind of makes sense to me. Eh? Could you upload the PDF? Yes, I can. You want to? Yeah, give me a second here. I'm just going to upload that. Do I have it? Oh no. All right, here. Give me a sec here. There we go. Here is the. Here's my class. You don't see my screen, but I'm looking at. I'm just going to upload that for you here. Content and lectures. Show more. So it's going to be after 23, and let's get the lectures here. There it is. So I'm going to give you 24 and 25 lectures. 24. Actually, give a PDF version of it so you can see it easily. 24. Done. And let me give you 25 as well. May as well. 25. And done and done. Thank you for reminding me. Okay. All right. So you can open it up and I can follow those lectures here. All right. So slip range. We're talking. Okay, as a generator. Okay, so if we use the wound rotor and we use the machine as a kind of a generator configuration, let's see what we're going to have. In the generator configuration, the rotational speed is going to be bigger than the synchronous speed, of course, because we're applying the power the other way. All right, so we're applying something more, and we're always going to get something less because we're always going to have losses. All right, so the rotational speed is going to be greater than the synchronous speed. So the slip, you're going to end up with a negative slip. All right. So if, in other words, as a slip, you can ask how much, in order to describe the slip, you can say, how much slower is the rotor turning from the synchronous speed? Well, if the rotor turns faster than the synchronous speed, then you're going to end up, it is slower as negative, it's negative slower, which is faster. All right. So we're going to get with the negative percentage values when we use the when we see the motor or generator. So in motor, you're always going to end up with a positive slip, which means the rotor is going to be turning slower than the synchronous speed. And if we reverse the situation and try to use that in a generator configuration, that machine, we are going to end up with a negative slip, which means the rotor is going to turn faster than the synchronous speed. All right, let's take a look at some currents here. Let's get the idea of approximating full load current. Okay, now we're talking about the nominal values, which means that nominal value is a value that something is designed to work as. So we have a formula here. Just get rid of the other mouse because it's annoying. You don't see it, but I do. Okay, so this one here. The current, the line current, is equal to 600 times power over the line voltage. And in this case, we are going to apply the power in horsepower. Right? So here's the P with a little h. Right? Rated power. Okay. And here's that number 600. Okay. This 600 is something that is called a empirical value. What is an empirical value? Empirical value is a value that is determined by experience, not by calculating pure math. Right? So yes, of course, pretty much everything can be expressed as a mathematical equation. But in reality, if you really wanted to express the mathematical equation, you would have some sort of a mind-breaking, brain-twisting integral to solve. So as a rule, the full load current is going to be 600 times when the motor is at a full load. All right, so the current is going to be 600 times the line current, 600 times the horsepower divided by the line voltage. All right, so the I here stands for the full load current, and it is in amps. The power, the PH here, it's a power rating, and it is in horsepower, right? And the E stands for the voltage rating as line voltage. All right, so that's what you would see on the nameplate. All right, voltage rating, line voltage, and of course that is in volts. Right. There are some other empirical values that I'm going to talk to you about right now, and you can probably see it. Starting current and no load current. Right. So we have the nominal values, as the machine is rated, the motor is rated to work at a full load. So the rating would be here, the power rating. It's described in horsepower. And we can calculate the full load current based on this formula and based on the numbers that you're going to see on the nameplate of the motor. So the current at the full load, that's the formula. You can either remember that, or you can remember where to look for it and or how to look for it. So based on that, there are some other empirical values. The starting current is going to be 6 times than the rated current. And the no load current, excuse me, it's going to be about 30% of the rated current. Again, these are the empirical values here, which means it's just the way it is, in other words, okay? So if you remember those, then you can do all kinds of calculations or predictions on how the machine is going to run. All right. Now, why is it? Why are those values the way they are? All right. Well, as we remember, as soon as we apply power to the stator, the magnetic field does not take its time to bring itself to the full speed, because philosophically it could, but in reality that we operate in, as far as this scenario, then the magnetic field has no mass. So as soon as the power is applied to the stator windings, that magnetic field is going to start rotating at the full speed right away. Okay. So when that happens, it is going to try to bring the rotor to full speed as quickly as it can. Right? It asks, there is no mercy. It's going to just hit that rotor, and it's going to be hitting it with a full force until the rotor gives in and start turning the way that the rotating magnetic field wants it to. Which means in the beginning, there is going to be huge difference between the rotating speed and the synchronous speed, which means it's going to be the greatest amount of change in the magnetic field that is going to hit the conductors, either the metal bars in the squirrel cage or the windings. So of course, when you have the greatest change in the magnetic field applied to whatever the conductor is, it is going to create the greatest EMF, which is going to, of course, create the greatest current. So the starting current is going to be huge. It all makes sense. And then when the rotor gives in and start rotating, you only need as much as to maintain the speed. Right? And at the full load, if the machine is loaded fully as rated, then you are going to have whatever it is rated for. And we have the formula already, okay, which is the 600 times the horsepower over the line voltage, okay? And then when you have the rotor at a standstill, you're going to have as much force applied to it. So yes, it's going to create a huge amount of current. And then when the rotor is being brought to the full speed, full rotational speed, not the synchronous speed, because it's always going to be less, remember? Then you only need as much power as to maintain it. Same as if you sit on a bicycle, right? And you really want to start as fast as you can, you are going to push on those pedals. And once you get to the speed, all right, that you want, you're just going to pedal as little as you need just to maintain the speed. So here's the same thing. Same if you're driving a car, when you want to really rip it with the car and just start drag racing, okay? You push the pedal to the metal, and then once you get the speed, you take a little bit off just to maintain the speed, all right? So that's the same kind of idea here, okay? So here is an example, example number 2. All right, so a three-phase induction motor has a rating of 500 horsepower. Remember the units. Units are important, okay, because quite often you're going to get the machine as a motor, you're going to get the rating in horsepower. And if that machine can be used as a generator, you're going to get the rating in, let's turn this thing on, the rating in watts. All right, so that would be your, I wasn't with you at that time, but you had it with Mr. Liu, your very first lab when you were running around the lab room and getting the information from the nameplates of the motors. You probably remember that when it was when the machine, there are two nameplates, one if the machine was used as a generator, one if it was used as the motor, and in one you would have a horsepower as a generator, sorry, as a motor, and if you had the thing as a generator, the power would be listed in watts. And of course the power is power, all right? It's those horsepower and the horsepower and watts, Newton meters, whatever else. Power has many units. They are convertible, right, from one to another. Okay. Now, if you look at the horsepower, between horsepower and the difference between horsepower and watts, if you want to convert that, it is not going to be 600. Okay, it's going to be a different number that you have to apply. So it has nothing to do with the power conversion from the watts into horsepower. That 600 here, it is what it is. It's an empirical number, which means it is determined by the experience and as things are observed, rather than pure mathematical calculations. Okay, so let's see here. A three-phase induction motor has a rating power of 500 horsepower. The line voltage. Okay, so here's the just okay. So 2300 volts. Right. That's it. 500 horsepower. So that automatically you should know that this is the line voltage. Right. So this is between the two lines, not between the line and the neutral. Right? So that's a 300. So that's 2300 volts. That's a line level. Okay, line level voltage. Calculate the approximate values. See, now we're using the word approximate here because we're using those empirical numbers and we're having those assumptions based on the experiential facts. Okay. So calculate the approximate values of full load current, starting current, and no load current. All right, so full load current you can calculate first, right? So there's the formula, 600 times the horsepower times the line voltage, blah, 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 kaboom, you get 130 amps as a line current. Okay, so then you can expect if the motor, if you apply the electricity or apply the power to the motor as the motor stands still, you are going to have 6 times that than the full load current. So, okay, so that is going to be a lot of current. If the motor is running normally at a full load, which is what it's rated for, at 130 amps, when you push that button, remember when we were pushing the button on this, well, it was a synchronous motor, but remember the synchronous motor is not self-starting, not self-started, not self-starting motor. How do we start the synchronous motor? We started as a asynchronous motor first, or as a squirrel cage motor, or our induction cage motor. It's induction cage, as induction motor, right? And those motors that we have, they have wound rotors. Okay? So the synchronous machines, right? The ones that we're going to be using in our very last lab, these are squirrel cage motors. So as you remember, when you were doing your very first lab, when you were familiarizing yourself with the machines and getting the bearings on things, learning the ropes, that squirrel cage motor did not have 2 nameplates. It just had a nameplate for the machine to be used as a motor. Right? If you want, you can just go back and review your labs, and you're going to just say that what I'm saying is true. All right. All right. So where were we? All right. Full load current 600. So then you can find out the approximate value of the starting current, and if the motor is not loaded at all, it's just not engaged in doing any work, you're going to have just a maintaining speed of making this thing turn, right? Which is going to be 39 amps, not 130, right? So remember when we push the button just to start the synchronous motor, those 3 amp meters that were measuring the current that is going that flows through each phase. Remember, those things swiveled sky high, all right? And then when the motor kind of settled, before long, those 3 needles got kind of towards like 40% of what it was, or maybe 30%. Right? It should be 30%, but yeah, you know. So that was the reason why those needles bend so high at the starting point, and then they settle down. Right. So here is the reasoning here. All right. So that's what we're talking. So because, and why is it happening? Because the synchronous motor that we were starting it as induction motor first. Right? And then just if you think about it, if you connect the dots between this class and the lab and the classes before, what's happening when you have that, because you can also have a squirrel cage embedded onto the router of the synchronous machine. So then remember, we had to disengage the excitation current from the field, so we don't put the machine through too much of a shock when we are starting that, and basically we'll be burning out the coils. Yeah, I just drew a blank. All right. So we're starting the. Yeah. Okay. There you go. I know what I was getting at. All right. So then that squirrel cage is engaged only during the start, and the motor is not as efficient as if it were when running a synchronous motor. So you're going to have that about 30% of the starting current. Right? Now, why did it go to 40%? Not 30% on those meters? Well, because when we were starting that, those meters didn't have enough scale. So we went beyond the scale and then just came back, right? So that's why, so once that machine runs as a synchronous motor, then we engaged the excitation field, which means we magnetized the rotor windings. Then the current dropped down, and then we could just adjust the current to accomplish the unity power factor. But what is happening with the squirrel cage that is still there, because that just doesn't disappear? Right? Well, that squirrel cage is turning with the same speed as a synchronous speed, which means the magnetic field that surrounds those metal rods is not changing. So that squirrel cage is just there, right? Not contributing, not subtracting anything from the equation. Right? Right, so we have gone through this slide, full load current. Okay, so we got, if we remember anything from this. So here's the formula for if you have the power rating on the motor, which you can get at the nameplate, and you know the value of the line voltage, and you know so then you can find out what the current is at the full load. Here's the key two words, full load, right? And that is, you're gonna have to remember that 600. When we do the test, you can keep the formulas, because I'm not going to expect you to remember all the formulas. You can have I hate to use the word cheat sheet, so I'm just going to refer to it as reference sheet, okay? With the formulas, and you're just going to have to know which formula to apply to what, okay, what scenario. And next week, we're just going to talk a little bit about because that's pretty much the only thing we have to cover is the variable frequency drives, okay? And then next week, after that, we're just going to go to a full review, and we're going to consider some examples and do some calculations so we can get you to writing the last test. And yes, you are going to have those formulas with you. In fact, it's going to be an online test, so you can find the formulas anywhere. Right? But if you were in person, yes, you would have the formulas with you. All right. So as a summary of this one here, you have 600, that 600 number, you have to remember that. That's if you're calculating or approximating the full load current. And then here is the relationship between full load current, here's the number 6, and here is 30%, which is 0.3. All right? All right, let's go here. Now, let's talk about torque versus speed. All right. The motor torque depends on the speed in induction motor. So Mr. Liu said here that there is no simple equation. Torque versus speed curve is presented here. I'm going to zoom on to that pretty soon. So if we are using this lecture, we're using Zoom, and we're going to zoom this picture here. So we're going to be operating at the zoom square, right? Right. Okay. All right. There was a slapstick. Okay. So rotor speed, torque, stay. Okay. At the locked, what do we have here? Torque versus speed curve, which is this one here. A full load torque is right here. Just going to zoom in and out. Right. So we have something. Here's the dotted line. Here's the nominal torque. And what's a nominal torque? It is the word nominal is basically a usual state of operation, usual operating condition. Okay. And over here, the torque, you could, here's a little dotted circle here, and it describes this point here as a full load. What do we have on the x-axis? From 0 to 100, and at this 100% here, that is our rotational speed, and at the 100%, that's our synchronous speed. All right. So there's no per se values here. We have percentage values. So that is going to, the real values are going to be dependent on the many things, that how the motor is supposed to be operating, what's supposed to have, but this is the percentage here. So it's like a reference chart per se. Right. So here's this is the rotational speed of the motor, and here is a torque. Again, there are no values. That little t, or the capital T, stands for the torque. And over here, the torque is basically at unity. So it's the value would be the 1 as a ratio, unitless. It has no unit. So it's a 1 torque, right? Torque, the torque value of unity. Okay. So over here, this is the full speed. And over here, see, that's the actual rotational speed designated with the letter N. So here is the full synchronous speed, and this is the actual speed that the motor actually turns. Right? Now, what else do we have here? There is, at this point, this condition is going to be referred to as a locked rotor torque, which means basically the torque stands still. The rotor stands still. So at that point, the torque that is applied to make that rotor turn, it is going to be equal 1.5 of what the torque would be when the machine is operating at the full load. So that's when you press the button to start. And this wavy line here represents the torque versus the rotational speed. All right, so here is, so if you remember when we pressed the button at the synchronous machine, because that's all we had, which was basically we were starting a induction machine, because we just talked about, right? Remember it was just the whole thing just started like a monkey with a razor blade on steroids. Okay, the machine almost shook when we pressed that button. It goes like boom, right? So that's the locked rotor torque. Now, then the machine applies a little bit less torque because it's kind of weakened. It's you know, oh wow, this thing is going to create resistance. So I don't know, it just made my muscles weaker. And at this point, it says, no, wait a second. We're going to bring you to the speed that we want you to be at. So then I'm going to apply as much torque as I want. So here's, I just reflected on things. You're not turning? No, I'm going to make you turn. So it's going to be a pull-up torque from here to here. And then once it's pulling up, it's going to apply more because well, if you use that analogy, it thinks that it needs to provide more torque than it's needed. It's just a way of physics, if I can say that, right? So it's going to, the pull-up torque is just going to be stronger, 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 and then it's not going to stop on a dime. So it's just going to go up. So the torque is going to be huge, and it's going to be the biggest torque. At this point, the machine reflects and says, oh, whoa, we don't need as much anymore. All right, so that thing, that rotor is actually cooperating with us. So at this point, I'm going to decide that I'm going to apply less torque, and I'm just going to lower the torque until we reach the point when we are all operating at the full load speed, full load, and then we're going to maintain the speed. So that's how this curve works. And if you remember, if there are any musicians with perfect pitch here and some sound, audible memory, you'll remember when you push that button, how did it sound? It's something like something like that, right? So here it is. Right. Okay, don't quote that, right? It's not going to be on a test. But if I could just, if I could visualize that as an audio. Now, pay attention to the sound that is going to be making once you press the start button on the induction machine that we're going to be using. All right. So let's zoom out a little bit. Let's see what this slide says here. Okay. So full load torque. So here we already have that. Locked rotor torque. At the standstill, the rotational speed equals 0. Breakdown torque. So here is the breakdown, the moment of breakdown. Right. So the torque goes up and up and up and up, and then the machine decides, oh, we don't need to use it as much anymore. So I'm going to start lowering it down. So this is the point. So this point, the breakdown torque at the induction machine is going to be 2.5 here. 2.5 of the full rotational at the torque that the machine works at the full load conditions. Okay. So the torque here, the unity torque, is as a reference here for us to use at the full load. So that's going to be the maintaining torque. Okay. I think I have a little bit. There you go. That's better. All right. So the torque is going to be at its maximum value ever at the point when it reaches the breakdown, not at the starting point. Notice that. See that? At the starting point, the torque is only 1.5 greater, 1.5 times greater than the torque that's applied at the full load. Right? You got that. Right? So at the normal conditions, right, the speed is going to be greater than the speed at the breakdown position here. Okay. Of course, it's going to be greater. See, there is a speed, the normal speed at the normal operation. So that's the point here. So if you look at this point right here, and if you look at this an equation here, all right, or this relationship, you are going to see that the torque, the speed is at this point, right? Which is less than synchronous speed because the synchronous speed is here. That's 100%. It will never reach, right? The rotor is never going to reach the rotational speed, and it is bigger. The torque is bigger, or so the speed is bigger than the speed at the breakdown point. Right? So here is when it reached the speed. This is just about to reach it, and when things are being decided, no, we don't need that as much torque. So here's the speed. So, and when when the machine accelerates, right, which is basically it's picking up the speed. The rotational speed, of course, is going to be greater than 0. And when it accelerates, it's going to be smaller than the breakdown torque. So there you go. So here are the relationships. When you download this thing, look at it, stare at it, listen to what I just said, and nobody's gonna get hurt. Okay, whatever. All right, let's see what else do we have here. Hey, so it's going to be a summary of whatever we just learned right here. Let's see what we have. Slip. Slip is equal to the synchronous speed minus the actual rotational speed divided by the synchronous speed, and we're going to get a fraction, unitless number, and if we multiply it by 100, we're going to get the slip in a percentage, as a percentage. And then the current, right? Approximating the current, approximating the approximate values of the current. At the full load, here is the formula, and you just have to know that it's 600 and that's it. All right. So this is the what's called the empirical value. And remember, empirical value is the value that is determined by the experience and how things behave, observation of the reality, rather than trying to figure it out with the pure math, okay? So here's the 600 times the horsepower. And what's that? That's the rated at the machine. That's the rating of the machine, right? So the machine is rated to operate at 600 horsepower, right? If it's a motor. And as we remember, the machine will operate the smoothest and the most efficient, always, at its rating power. If we operate the machine at half of the rating power, the machine is not going to be as efficient. It will still work, it will still do the job, but it's not going to be as efficiently, which means we're going to have to put in more power than we're actually getting the power out. And if we operate the machine at greater than its rating power, then the machine is also going to be not very efficient. Well, so that's the relationships here. So at the full load, here's the 600, and when we are starting at the moment of start, we're going to have the current claim to about 6 times of whatever the rated current is based on the full load. And if the machine is operating at no load at all, it is going to operate at about 30% of what the full load is supposed to be. Okay? Watch those meters, those 3-phase meters, the three meters of the that are measuring the current for each phase. Remember, we're connecting those to the windings, the stator windings. Watch how they behave. And you're going to see something like that in reality once you push that button. All right. So in the torque versus speed curve here, we are considering something as starting torque, breakdown torque, and a full load torque, and is basically what we talked about right here. Okay. You can go back if you want. All right, so it's over. All right, I like Mr. Leo's graphics here. Pretty nice. And here are some references if you want to kind of retain the information that I just gave you. Now we're halfway through. Do you guys want to take 5 to 7 minutes for a break? Make yourself new coffee, get rid of the old one, and go refresh or not? Just let's just take a couple of minutes. So it is okay. What's the phone say? What does the phone say? Oh, it's 4 o'clock right now. Okay, so give ourselves 10 minutes. We're going to come back in 10 minutes. So that's going to give you some time to refresh. So not on the PC, not on the other, on the clock on the wall, on your phone, because the clocks are synchronized. 10 after 4, we're going to resume the class, and I'm going to press the pause button, and I should play you some music, I guess. All right. Resume recording. So now we are back online. Back is back. All right. Okay. Second part of this class, and at the end, I'm going to give a little bit of a spiel on what to expect with the last lab. So you know what to expect there, okay? All right, so we have here induction motors part 3, okay? There you go. So we're gonna review classification, power flow, and a summary. We always talk about summary, okay? All right, so as we talked about here as a review here, slip is basically the slip talks about how much slower the rotor actually turns in relationship to the actual synchronous speed. And what is the synchronous speed? The synchronous speed is the speed in which the rotating magnetic field revolves. Okay. All right, so that's the slip. Here's the formula. Okay. Then we have approximating currents. Remember that the 600 empirical value. Empirical value for the fourth time is the value that is found by experience, not by the pure math. Okay, and empirical value it is because that's the way it is, and that's it. All right. So here's the 600. So at the full load with the induction motor at its full load, when it's loaded fully. And what do we mean by fully loaded? Does it mean that we load it as much as we can and so it still runs? No. A full load is the load that the machine is designed to operate at. Okay. Or at which, okay. So we got that out of the way. So here's the current, that the full load current from the nameplate, and for a nameplate you can see the rating of the machine. All right, so whatever the rating it is, multiplied by 600, divided by the line voltage, not the phase voltage, the line voltage, and you're going to get the current. Right? And when the motor starts, the current jumps up 6 times high at the starting position as soon as you press the start button. So there's a bit of a shocker to the machine, and it has to be designed in a way that it withstands that. And at the no load condition, the current is going to be at about 30% of the full load current. All right. And then the torque versus speed. We're talking about the starting torque, breakdown torque, and the full load torque. The full load torque is our reference here. And the breakdown torque is when the machine is going to apply as much torque as it thinks it should, and it's just going to get out of hand, but then it's going to reflect on things and say, oh, maybe I shouldn't apply because, you know, this rotor is beginning to cooperate the way I want it to. So I'm going to go easier on that rotor, and I'm going to not push it as much because I don't need to push it as much to get it into the nominal speed, so that when the machine is supposed to be working at, or the nominal condition. All right. So then there's a starting torque. Okay. And here is the relationship between these things. All right, so we talked about that. All right, cool. Let's keep going. Classification of induction motors. All right, here's a bit of a table here. All right, we got four classes of the induction motors. We got class A, B, C, and D. And we have, according to that, we have something that is called a torque versus speed curves according to the classifications of the motors. So here is class A, class B, class C, and class D. What do we have on the x-axis and y-axis here? So over here, it is the torque percentage of the full load torque. So here is the 100% of a full load torque right here. And if you keep going, keep going, keep going, you're going to hit those curves, right? And you're going to see that the class A, B, and C, they will operate in a very similar way, okay? And class D kind of is a loner right there. It just deviates from the crowd, okay? We're going to talk about those things. And over here is the speed percentage of a synchronous speed. So over here is a synchronous speed, all right? And here is the 100% of the torque at the full load. And from this graph, you can say that it actually makes sense. Oh, I'm getting those thing appearing here. You can see that at the full load, of course, the speed is always going to be, if we use it as a motor, the speed is always going to be less than the synchronous speed. So you know what? So far, so good. Things do make sense according with the reference of what we talked about so far. All right. And we have the silly phone ring happening. We're just going to wait until that thing stops, and it just stopped. Most annoying thing. Whoever uses music for the phone anymore. Anyways, you gotta like it. All right, so here is a little table that classifies the motors according to the starting torque, starting current, and the slip. Now, you don't see, you have sort of like arbitrary type of terminology here. And this thing is using high, normal, high, low, or whatever. You're not going to have, it is impossible to put real numbers here because you're going to have small or big motors and really small motors and really huge motors. So the values here are described as high or low, which is basically, comparing to the others. It's a comparison type of a chart, all right? So in the class A, we have starting torque as a normal, so that's going to be our reference. So it is what it is in class A. So here is the curve, right in the middle here, that's the curve. And you can just analyze it at home when you have nothing else to do. All right, and then the starting current is going to be high, and the slip is going to be low. There's not going to be much of a slip, which means that the rotating speed is going to be pretty much very close to the speed or the synchronous speed. Okay. Now, class B behaves a little bit different. We still have the normal starting torque, and the starting current is going to be slightly lower than the class A. And again, we're going to have a speed, the slip, low slip, which means that the rotational speed is going to be pretty damn close to the synchronous speed, right? Then it's class C. Then we got a high current starting. Sorry, we're going to current. We're going to have a high starting torque. It's just going to rip it. all right? And we're going to have low, in both cases here, we're going to have low starting current, class C and class D. And we're going to, in class C, we're going to have a normal. So we're just going a little bit more than the low and a little bit less than the high slip. And the class D, same as class C, high starting torque and the low starting current comparing to the normal. And you are going to have high slip, which makes sense. If you look at the class D curve right here um, uh, at the full load condition here, 100% of a 100% of a torque applied at its rating at the machine, the way machine is rated, which is supposed to operate. Then you see class D has the biggest slip of them all, which means the difference between the actual rotational speed or rotating speed is going to be the biggest comparing to the other three classes. The other three classes, A, B, and C, are quite comparable with each other. All right, now I'm going to interrupt this here, and I'm going just prepared a little. Where is it? Here. All right. The uses of that uses, because you might say, where do we use those machines? All right. Class A motor. So as a reminder, it has a normal starting torque, high starting current, low slip. It's a highly efficient motor, and applications, it can be used in fans, blowers, or small pumps. Okay, so you would use mostly class A motors. Class B motors, it has a normal starting torque, low starting current, and low slip, and mostly in class A, in class A applications. You can be more prone to use that in voltage starters, and you can research what a voltage starter is. And the key idea for that is that it has a lower starting current, so it doesn't put too much shock on the voltage starter, which is the device that starts the motor. Okay, so but mostly in class A applications. Class B and A are pretty much the same uses, which would be fans, blowers, small pumps. Then the class C motor, it would have a high starting torque and low starting current, and that would be used mostly in compressors, conveyors, reciprocating pumps, and crushers. So you are getting what can you tell about this? Conveyor, that's a continuous operation. Pump is mostly, the reciprocating pump is mostly continuous, but it actually reacts to the conditions. So you need more starting current. So just like if you were riding a motorcycle, if there are any motorcycle riders in class, but I'll just use that motorcycle analogy for this one, is that when you have a motorcycle that is low powered, you might want to just cruise it around and just some secondary roads and just drive around the city and whatever. But if you want to get the motorcycle on a highway, then on the highway you're going to experience some little bit more extreme conditions that require you to provide a lot more power at the moment noticed when you need it. Okay, so that would be the kind of a class C type of a thing. All right. So that's as far as comparing things, as far as I can do that. Now, class D motors, here it has the highest starting torque, all right, low starting current, and high operating slip. All right, so highest slip, and it's not as efficient as the other ones, but what we need to have as much punch as we can get out of that machine. So that's why this motor could be used in punch presses or bulldozers or die stamping machines or high impact loading. So as you can tell, that these applications would be applications that you just need to get as much, if you can call it, punching power out of the machine. All right, and I'm going to also upload that, so you could just have that little thing with you. But if you want, you can also, there's always Google, as long as I mentioned that to you, so you know what to look for. And I'm pretty sure you would find that out anyways, because you know we have this class A, B, and C here. And let me just bring it to the full screen like that. My first question when I looked at that was, okay, so that's nice. So, all right, so where do we use those? All right, so I told you. I just told you here. Okay, and here are the curves. Look at this slide, stare at it, see what settles in your brain when you look. And here's the thing: if you have ideology type of slides here that talk about the concept, the conceptual type of slides, sometimes just reading it once or twice doesn't cut it. You have to keep coming back to it, and that's the way you know, our human brains work for the most part. So that's why it's quite often quite often the technologically tech-savvy people will develop a habit of slow reading as opposed to academic, as far as reading books or journalists. They will be the fast readers, and we, because we need to read it again and again and stare at it and contemplate on it, we develop a habit of slow reading. All right, nothing wrong with either of them. All right. So this is selection of motor according to the applications, starting, torque, and slip, and I just basically gave you that. All right. Now let's talk about the power flow in these machines here. Power flow of an induction motor. Input power. What do we get? Stator AC power. That's all we get. And we don't need to supply any power to the squirrel cage, and we can't. All right. We are not supplying any power to the wound rotor. We just have to short things out so it acts as a squirrel cage. And if we want to get something out of it, if we use it as a generator, of course, we're going to unshort those windings at the common point, and so we could just get something out of it. All right. So here are the relationships here. The input power is basically the AC power that we applied, and you can have the 3 times phase voltage, all right, times the phase current, because we have 3 of those. And then because we are dealing with the AC conditions, then we're going to talk about the cosine of a theta, and we can expand on that later, or you can just refer to the previous lectures that we had. It has something to do with the angular velocity of the conductor versus the changing magnetic field, right? Now, or it could be square root of 3 times the line voltage and the line current times the cosine of the cosine theta. All right. So here's 3 times phase voltages. If you look at the phase voltage and phase current, or that would be in the Y configuration, considering the Y config connection, or if you're talking about the lines, which would apply mostly to the delta configurations, we're going to use that kind of a relationship, right? Output power, and out of the motor, the induction motor, of course, we're going to be talking, because we're using it as a motor, we're talking about the output mechanical power on shaft. Shaft is the axle that basically is in the middle of the rotor, right? So that's the whole idea, to make the shaft turn and make that shaft, well, power from that shaft applied to other things that are supposed to turn or go sideways or whatnot, depending on the mechanism you're going to use and apply to that shaft. All right, so output power is the mechanical power, and this is a good old formula that we have used already. We have the torque times speed over the 9.55, all right, and that is another value that we talked about, the empirical kind of a value here, all right? Now, losses, the loss would be if you subtract the whatever you have to put in and whatever you're able to get out of that, and that is going to be the loss, how much power was lost to operate the machine, right? And mostly, where does the power get lost? Well, there's heat being generated. Then there's going to be some friction, and there's going to be some, well, we're not doing any field excitation, so we don't have to include that. So here is the input power and the output power. And if it was a synchronous motor, then we have to add to the losses, or, well, yeah, it's going to be added to the losses because it's going to be added to the input power, right? But we are not using field excitation in induction motors. Right? And the efficiency is represented by the Greek letter mu. That's what it looks like. It looks like a n that went wrong. Okay, and it's the efficiency. It's a fraction of the output power versus the input power. And of course, if you multiply it by 100, you're going to get that fraction in that number represented in percentage here. All right. Let's see how many slides do we have here. All right. Now, here is what we're going to talk about right now. The two power meters, three phases, 2 meter, three phase power metering on if you want to measure the power. If you use the electric power meter electrically, okay? And I'm going to switch to my screen here. All right, so here is what we're going to have. We have three phases, phase 1, phase 2, and phase 3. All right. Let me just lower the light here so you can see things better. You don't need to see me as much. It's almost like I'm going to teach you music here, all right? But no, there's phase 1, phase 2, phase 3. And what is the power when we look at the electrically, if we want to have the relationship of whatever quantity with whatever other quantity to determine the power? We could have voltage and resistance, you could have current and resistance, or you could have voltage and current. Based on those, what I just said, you can calculate the power. All right. Now, we're talking about and here we're going to talk about three-phase, two power meters, three-phase, 2 power meter power measuring method that is dissipated by the whole system of these three phases. Right? Now, if you had 4 phases, if you had 17 phases, which is not likely, you can also determine by this sort of scenario what I'm going to show you. So here's what we're going to do. Power equals, let's say, here, power equals voltage times current. So you could apply the current meter across in series with all the phases, but you know what? There's another way that somebody smart found out of how to do it. So if we interrupt any two phases, let's say the top two, right? But it could be any of those. We interrupt those two phases, and we're going to put an amp meter here and an amp meter here. And we're not going to apply the third one because we only have two of those meters. But what is a power meter? This is just an amp meter. Well, the power meter is just like having an amp meter and a voltmeter in one. So let's say we're going to have a voltmeter here and a voltmeter here, which that is going to be part of the first power meter, and this is going to be part of the second power meter. So here's a unit, here's a box, and here's a box. Now we have put those 2 amp meters in 2 phases, any of those phases. Now, the trick is to pick a reference, and we already picked a reference because this is the one that we are not going to use the amp meter on. And that is going to be our reference to our voltmeters. So both of them, both of those voltmeters, I'm going to draw a line here, jump over, and connect to that our reference. And the other one, we're going to do the same. Just here, jump over this one here, jump over that one there, and connect that to our reference that was picked by us, and that's the one that we didn't put the the amp meter. And the other side of the voltmeter, one of them is going to go to that one here, and the other one is going to go to that one here. If you connect these power meters in this way, then this box is going to have a dial. Oh, the dial looks like here, all right? All right. And it's going to have some scale on it, and it's going to have a needle that is going to point at the scale, and here is our readout, all right? So this box is going to have one of those readouts, and that box is going to have one of those readout units, and this scale here is going to show power in whatever units, but it's going to be in watts, okay? So this meter is going to show certain amount of power. That meter is going to show a certain amount of power based on these connections, and that basically that box is tapped into the in series with the line here, and that box, the amp meter part of that box, is tapped in series when with the this line. And these voltmeters are measuring the voltages between this and that, and this and that, according to the, and this is going to be our, that's not a reference, that's not a ground reference, that's the reference for that voltmeter, and for that voltmeter, that is the third phase. Yeah. Now, if you read what this one shows in power, and if you read what this one shows in power, and if you add those two readings, you are going to have the full power that is dissipated by this whole system. Yeah. Take a look at that. All right. So that's basically the idea. Now, when you are going to try to find out, you can use that method with any number of phases. all right? And it's going to how many power meters, and each power meter is going to have 4 connections, all right? It's going to have, okay, amp meter will have 2 terminals. A voltmeter is going to have 2 terminals. An amp meter is going to have, okay, got it. Right now, a power meter is going to have 4 terminals because you need to measure the power and you need to measure the voltage that's applied to whatever the element is, and the calculation is going to happen mechanically or mathematically inside that box, and it's going to give you the power, which is going to be voltage times current, and that's how much the needle is going to swivel for that. Okay. So if you notice, you have 3 phases, 2 power meters. Right? Now, if you had 5 phases, you would need 1 less power meter. So if you had 5 phases or 5 lines, you are going to need 4 power meters. If you had 17 phases, which is completely out of cosmos that I'm getting those numbers, if you had 17 phases, you're going to need 16 power meters. So it's always going to be 1 less. Right? And then you can measure it that way. And if you just add these 2, all right? So this is the power meter 1, power meter 2, power meter, not R, it's a power meter 2. The total power, in this case here, equals to the reading, right? Coordination, that's called a hand-eye coordination. It's getting towards the end of this term. Everybody's tired, including my brain. All right. So in this here, the case, the power, total power is going to be equal. It's going to be equal. It is equal to the reading of the power meter 1 plus the power meter 2. And at some point, you're going to have a negative power reading on one of those, depending on what the conditions are. If you have in one of those, the power is going to show negative. That's the trick to those. You still add those. So if this meter shows 10, and this meter is going to show -2, so you're going to go 10 plus -2 is going to be 8, right? And you're going to experience those conditions when you're going to perform that last lab, right? So we pick one as a reference. You stick the ammeters in series to the other 2, and that reference is going to be the reference for both of those voltmeters. And one of the voltmeters is going to measure this voltage between this line. The other meter is going to be measure the voltage between these 2. Now, all right, so here's the example. I'm going to encourage you to kind of follow the example here, analyze it, and maybe we can tackle that here. So basically, this is what I just showed you, is this. Okay, what do we have as a reference here? What do we have as a reference here? This one here, we picked the reference as the middle one instead of the bottom one. See that? Over here, in this example here that I still have on that sideboard, in the picture we picked the reference of the bottom one. You could pick a reference as a top one, but the whatever the reference is, it's not going to have an ammeter in series with it, but it's going to serve as a reference to one of the voltmeters and the other one. So both of those voltmeters are going to be taking the reference from that. And the other side of the voltmeter over here is going to be plugged into that line here, and the other side of the voltmeter is going to be plugged to that line right here. Right? So one meter measures this voltage, the other meter measures this voltage. And whatever so obviously you can tell that these two terminals are the voltmeter, part of the power meter, and these two terminals are the amp meter of the power meter. All right. Okay. So the total phase power, it's kind of confusing because it shows as P3. Okay. That P3, that suggests that this is the power dissipated by, or power used in all those three phases. It's not the power of the phase 3 as compared to power of the phase 1 and phase 2. No. It's the total power of the three phases. Is going to be the sum of whatever one of the power meter shows and whatever the other power meter shows. And when you have that downloaded, you can look at that and you can stare at this. And you can stare at this relationship here and this relationship here. And at one point, it's going to hit you and it's going to enter your bloodstream. All right. So in this scenario, I picked the bottom. I picked the bottom phase as a reference. And in this scenario here, the middle phase was picked as a, it doesn't matter which reference, which one you pick as a reference, but you connect the stuff that the way I just showed you. All right. Now, here's an example that shows here, three-phase induction motor is powered by 60 hertz power system. The input power is measured by two single-phase power meters. They read 1.5 kilowatts, and the other one reads 1.3 kilowatts at 8:55 p.m. It outputs, calculate the input power. So it outputs the torque. So, okay, so what do we have here? So calculate the input power, output power, losses, and efficiency. How can we get, okay, so we got the frequency, we got power meter 1, power meter 2 indication here showing. We have the speed, 855 frames, we have the torque. Okay, so how can we calculate the power that is being put in to the system? Well, we got those two power meters, so we could add those two, and it's going to give us the 2.8 kilowatts because this one shows 1.5, the other one shows 1.3. So 1.5 plus 1.3 is going to give you 2.8. All right, so that's the 2.8 kilowatts that is being used to power that machine. And then the output power, well, we can use the torque and the speed because we have it. So that's torque times speed divided by 9.55. And you plug in the numbers, you're going to get 2238, so 2,238 watts, which is basically 2.238 kilowatts. If you want to kind of have the same unit and the same multipliers. So losses, well, you have those two numbers, you subtract one from the other, and the losses are going to be 562 watts. Does that look familiar with some of the labs that we have performed? Look at your data, look at the calculations. You're going to have similar values there. And then the efficiency, of course, is going to be the ratio between the output power, which is always less, and the input power, which is always more than the output power, because we have losses. That's always, or if you have it the other way, then you get the Nobel Prize. Talk to me, I want to be a friend. All right. And then you're going to get a fraction and multiply it by 100, you're going to get 80% efficiency. So that's pretty good, all right? So that's how you analyze that one. Okay, summary. we have talked about the classes A, B, C, and D and their uses. And this the motors are classified based on the torque, starting current, and the slip, and the power. Okay, power flow. We just talked about how to use 2 power meters to measure 3 phases. Okay, if you had 5 phases, how many power meters would you need minimum to measure the power? It will be the one less than it. So if you have 5 phases, you're going to need 4 power meters. If you have 23 phases, which is really ridiculous, you're going to need one less, which is going to be 22 power meters. Okay, so start saving money so you can get a lot of power meters. Okay, all right. And here is the diagram, colorful diagram of the power flow. And this IM stands for the induction motor. So here's the power, AC power applied. Here's the mechanical power that we're getting out of it. And we get some leakage in terms of losses here, all right? So you can get the references and all the reading materials of that. Let's just quickly take a look at the lab before we go. We're almost done. Just bear with me for about 2 minutes. Where do we have that? I have it somewhere. I have it somewhere. Lab 7. That's the last lab here. So based on that, you can use the prep. And if you are having problem with the prep, we're going to cover that in the beginning of the lab. But try to fill it out by yourself. Get your thinking juices flowing there. All right, now when induction motor draws 2 kilowatts, 2 kilowatts. Oh, well, here's 2 kVA. All right. So that should tell you something, and try to figure this out, see what that means. And if you have a trouble, then oops, here, Control L for the full view. And yeah, all right. Then talk to me and I will get you to the right direction, but try to figure out by yourself of what the current should be, the line current here. All right. Why is the line current? Well, we are going to apply the 3 phases into that, and there's not going to be any neutral supplied into that. So we're just going to supply, same as the synchronous motor. We're supplying phase 1, phase 2, phase 3. Were we connecting the neutral to anything? No, that neutral just was left all by its lonesome. Okay, so right, and then when induction motor outputs 5 kilowatts mechanical power at that 1752 RPMs, which is less than 800 RPM, so 1800 RPMs. You see that? Here's a hint, not a hint, but it kind of makes sense because we're using the induction motor, not the synchronous motor. So of course, the synchronous speed is going to be 1800 RPMs, but that rotor is never going to get there because as soon as it gets there, the rotor it's not affected by the magnetic field because it's not being hit by a changing magnetic field because it's rotating with the magnetic field, right? So you can calculate that. So basically, the purpose of this line number 5 is how much should we load the whole system before so we know that we're operating at that 1.5 kilowatts. All right. Then of course there's the instructor's signature. Now, if you look at the diagram that we're connecting here, just look at this. We have that machine, that little lab contraption that we have, is going to have 2 power meters on the panel there. And if you look at these connections here and the way things are connected in this whole picture, you are going to find, if you trace those connections, if you trace everything to the T, you are going to come up with this kind of idea right here, which is the 2 power meters, 3 phases. This is the same thing. It's just those lines are drawn a little bit differently. Okay? So when you see something complicated as this here, now I just uncomplicated that for you, because now you know what that is. You're not just going to connect the dots. Now you're going to understand what is actually happening in this whole system. So you know what you're doing instead of just going through the motions. Now this is the DC machine, and we're going to connect it in the same way as we did that. We're going to use that as a generator, and then we're going to apply the load bank to it in order to make it work harder. So we're going to make this induction machine work harder, and we're going to take a look at the slip, and we're going to take a look at the whole power supplied. Basically with this lab, we're going to confirm everything that we just talked about this in these 2 lessons, or the 3 lessons, the induction motor part 1, part 2, part 3. And this here, this lab is just going to confirm what we learned. Is it true? Well, of course it's going to be true, but now you know how to, okay, here's the speech I'm giving you right now, all right? Okay, so this is the end of today's lesson. Next time we're going to cover just variable frequency drivers, all right? If you want, you can just research it on your own a little bit, because I'm giving you a heads up, because I'm going to give you a riddle to solve, another riddle to solve. If you don't want to, that's okay, but you're not learning anything. Think about what I'm going to say, contemplate on that, try to come up with a solution, because that's when you're learning something, right? And the whole purpose of you coming here is to actually learn something that you could use once you walk through that door for the last time of our beautiful alma mater, which is our school. All right, and so what I'm going to say to you, think or try to research on your own variable frequency drives, and think about, in our lab room, do we have enough equipment that we could just grab whatever we want in our lab room, all these machines that we have? Could we create a simulation of a variable frequency drive? All right, so first thing, try to find out what the variable frequency drive is, how it works, what's the idea, and can we use the machines in whichever way you could think of to simulate the scenario of a variable frequency drive. Okay, so that's me encouraging you to learn. Okay, think that when you're filling out your student feedback. Anyways, that's it for today, and I'm going to see whoever I'm going to see, whenever I'm going to see, at the time I'm going to see. All right, thank you very much. I'm just beginning to go in circles now, and we just have one more lab to do, so see you when I see you. Okay.